Okay, so we finished the Euler forward method last time, and so this time we want to take a look at two other methods, um, and that is backwards Euler, and then we'll also look at improved Euler. You may be saying, why are we looking at all these Euler methods? Well, it's always good to have two different methods for solving the same system or solving the same differential equation, because then you can use the difference between those two methods as an estimate of your error. And so it's really good to have more than one method to solve these. We're going to talk more about error and estimating error in another section. But for right now, we're just taking a look at backwards Euler. And the idea behind backwards Euler is that we're sitting here at point Tn, right, Tn, Yn, and we're looking at using the derivative here at Tn, the derivative at Tn to to advance our solution. So we have a Tn plus 1 over here, and let's just say a Tn minus 1 over here, right? And what we said was that if I have my Tn plus 1 here, right, then we could write that y at Tn plus 1, or let me rephrase that. If we have y prime equals f of ty, I can approximate the derivative by using the difference formula. And so that would be y at Tn plus 1 minus y at Tn divided by the step size, or Tn plus 1 minus Tn, right? And so that would be approximately f of Tn plus Tn Yn, because I'm approximating the derivative here, right? And so I'm using this slope here to do that approximation. Okay, and so that means, solving this equation, then we get the normal version of Euler's formula. This is a different derivation than we had last time, but it's a valid one. Okay, the reason I go through that is because instead of using this forward difference formula, we could have used the backwards difference formula. Okay, so in place of y prime here, what I can do instead is I can use the backwards difference formula and write that y of Tn minus y of Tn minus 1 divided by h is approximately equal to f of Tn Yn, right? Okay, and so solving that, then I get y of Tn is equal to y of Tn minus 1 plus h times f of Tn Yn. Okay, now you might notice that something happened here. The Tn is here and the Tn is there. And so to put this in kind of the form that we're going to use it as, we'll rewrite this as y of Tn plus 1, which is our normal way of writing that. That's going to be equal to y at Tn plus h times f of Tn plus 1 Yn plus 1. You know what? Let me define that term. Define y sub n, right, as y of Tn. I think I've defined that before, but that'll make my notation a little bit easier. So let me rephrase this notation, because this notation I want to use. Y sub n plus 1 is y sub n plus h times f of t sub n plus 1 y sub n plus 1. Okay, and so this would be the formula that we would use for backwards Euler. But wait, you might be saying, the yn plus 1 appears on both sides of the equation. That's why this is called an implicit method. Implicit method. It's an implicit method because y sub n plus 1 is not explicitly defined in terms of the earlier variables. In fact, it appears on both sides of the equation. So what are we going to do about that? Well, there's actually two things we can do about this. Actually, there's more than that. I think we'll just talk about two of them. Oh, maybe three. We'll see how we go. So method one, in order to deal with this, we might get lucky. With the f of ty. And we might be able to algebraically solve the equation and get an algebraic solution that we can plug into our formula, our computer program. So just as an example, suppose that you're trying to solve y prime equals 4 times y numerically. You might be saying, well, why? Oh, maybe we'll make it a little more complicated. How about what, t plus y? It's not too much more complicated, but at least there's a t in there too. Okay, so and I want to use this implicit method. So just writing down this formula, right? I'm going to have that yn plus 1 is going to be y sub n plus h times tn plus 1 plus yn plus 1. But in this case, do you see you can algebraically solve for your yn plus 1, right? And so we could just solve for that, just subtract. So that's going to be equal to y sub n plus h times tn plus 1, which we know, presumably, plus h times yn plus 1. Just bring this over to the other side of the equation, and you're going to end up with 1 minus h yn plus 1 is equal to y sub n plus h times tn plus 1. Okay, and then just subtract yn plus 1 equals yn plus h times tn plus 1 divided by 1 minus h. Good. And now we have our specific formula for this differential equation only, right? And so that's what I mean by we might get lucky with f of ty, and then we could just hard code what the algorithm becomes in that case. What happens if we're not so lucky? Well, there's a way of approximating y sub n plus 1. So method 2 is to approximate y sub n plus 1 using Euler on the right. So what I mean by that, I mean yn plus 1 equals y sub n plus h times f of tn plus 1 yn plus 1 is the original, but then I cancel this out and I replace it by Euler's formula, yn plus h times f of tn yn. Right? And so that's another way to do it. So this is kind of nice because you know, you're using all the information there from Euler as well as the backwards slope as well. So that's kind of fun to try out. The last method I'll just mention briefly, and that is use a built-in function solver. And by that I mean like MATLAB, Octave, Python, they all come with some method, some numerical method to solve like some function of z equal to 0 for z. And so then the problem we would have is to translate our algorithm into this function g, and then we would plug that g into the solver that's built in. So just as an example, right, if we start off with yn plus 1 equals yn plus h times f of tn plus 1 yn plus 1, then yn is known, h is known, tn plus 1 is known. The only thing that's not known is the yn plus 1, right? And so let's call that z. And so my g of z that I would form would just be z minus yn minus h times f of t n plus 1 comma z. Right, so I would have to know what this is in order to plug that in. Algebraically, I would need to know what that is. Okay, and then you just set that equal to 0 and solve somehow using some numerical solver. But notice that when you're solving this, you're actually only getting one step, only does one step forward. So if you're trying to get a full approximation to your solution, to the y value, you might have 300 time steps to go through, and every time step is going to call up this solver and perform a bunch of stuff to try to find the solution to that. And so this could take a lot of time. Could take a lot of time. Depending on how complicated your function is and how many time steps you want. Okay, so in my experience, unless you have reason to believe that the derivatives are kind of hard to, or getting a little funky, or maybe hard to compute, Euler is always a good first step to try, just to see what the function looks like. And then we're going to get some more or some different methods later on. Boy, I've already gone to 12 minutes again. Geez, I'm talking too much. We still have to do improved Euler, so that'll be the next video.